Look up at the night sky on a clear night and pick a star, any star. Polaris, let's say. That light hitting your eye right now left its source 433 years ago. You are not seeing Polaris as it is. You are seeing Polaris as it was in 1591, when Shakespeare was 27 years old and hadn't written Hamlet yet. The star you're looking at may not even exist anymore. It could have exploded 3 centuries ago, and you won't know for another 100 years. Most people find this mildly interesting and move on. But I want you to sit with it a little longer, because something deeper is hiding in that observation, something that physicists worked very hard for about 50 years to understand. And when they finally did, the answer was stranger than almost anyone had bargained for. The strangeness isn't about light being slow, though it is 299,792,458 meters per second, which sounds fast until you realize the galaxy is 100,000 light years across. The strangeness is what the slowness of light forced us to conclude about time itself, about whether your future already exists, the way a city you haven't visited yet already exists. Let me build this carefully, because the popular versions get it wrong in ways that matter. Start with something you can do in your kitchen. You're standing at the counter and you clap your hands. Your friend is standing 20 feet away. You both agree. The clap happened at a specific moment. You both agree it happened at a specific location. No argument there. Now make the distances bigger. You're on Earth. Your friend is on Mars, about 20 light minutes away, depending on where both planets are in their orbits. You clap your hands. When did that event, your hand clap, occur, as far as your friend on Mars is concerned? The naive answer: the same moment it occurred for you. The moment you clapped, that's when it happened. And your friend on Mars just hasn't received the information yet. That's what Newton thought. He called it absolute time, a single universal clock ticking away, identically everywhere in the universe, so that every event has an unambiguous timestamp that every observer would agree on, if they could just compare notes fast enough. It's a reasonable assumption. It also turns out to be wrong. Here's where it broke down. In 1887, Albert Michelson and Edward Morley set up an extremely careful experiment in Cleveland, Ohio. The idea was simple. If light travels through some medium, they called it the luminiferous aether, then Earth moving through that medium should create a kind of headwind for light. Light going in the direction of Earth's motion should appear slower than light going perpendicular to it, for the same reason that swimming upstream is harder than swimming across the current. They measured it carefully, with an interferometer sensitive enough to detect differences of about 10 kilometers per second in the speed of light. The difference they found: 0. Not small, 0. Light traveled at exactly the same speed in every direction, regardless of Earth's motion through space. They checked the equipment. They ran the experiment at different times of year when Earth was moving in different directions. Still 0. This result made no sense whatsoever under the existing framework. Maxwell had just written down his equations for electromagnetism, 4 equations that contain essentially all of classical optics and radio and everything in between, and those equations predict a specific speed for light, c. 299,792,458 meters per second. But relative to what? If there's no aether, if there's nothing light is moving through, then what does it mean to say light travels at c? The answer that Einstein arrived at in 1905, at age 26, working as a patent examiner in Bern because no university would hire him. It means light travels at c relative to every observer. No exceptions. No matter how fast you're moving, no matter what direction, every observer who measures the speed of light gets the same number. This is not a fact about light. This is a fact about space and time. Here's why. If you and I are moving relative to each other, and we both measure the speed of the same light beam and get the same answer, then something has to give. Speed is distance divided by time. If the speed is identical for both of us, but we're moving relative to each other, then our measurements of distance and time cannot be identical. They must disagree in precisely the right way, so that distance divided by time comes out to c for each of us. This is where people's intuition usually fails them, and I think it fails for an honest reason. We evolved to deal with objects moving at maybe 30 meters per second on a good day. Your intuitions were not calibrated at 90% the speed of light, and I'm not going to mock you for having the wrong instincts. But let's see exactly where the intuition breaks. Take a clock, a real physical clock. Put it on a fast-moving rocket. That clock, as measured by someone watching from the ground, ticks slower. This is called time dilation, And it's not an optical trick or a calibration error. When the rocket lands and you compare the two clocks side by side, they genuinely show different elapsed times. The rocket clock has aged less. We've measured this directly. Not with rockets, we don't have rockets that fast, but with muons. A muon is an unstable subatomic particle, kind of a heavy cousin of the electron, with a half-life of about 2.2 microseconds. Cosmic rays hitting the upper atmosphere about 15 kilometers up produce muons. At the speed these muons travel, about 0.9997 c, even if they could somehow live forever, they should only travel about 660 meters in 2.2 microseconds before half of them decay. They should never reach the ground, but we detect them at sea level, in large numbers. The reason those muons are moving so fast, that time dilation stretches their 2.2 microsecond lifetime, as seen from Earth, to about 40 microseconds. They live long enough to travel 15 kilometers. From the muon's own perspective, by the way, its clock runs normally, but the 15 kilometers of atmosphere has contracted down to about 400 meters. Either way, same result, muon reaches the ground. That is time dilation, real measured with real particles that have a real internal clock. But here's the thing people miss when they hear moving clocks run slow. They think, okay, so moving clocks tick slowly, but real time, the universal background time, is still ticking away normally everywhere. No, that's Newton sneaking back in. There is no universal background time. Let me show you what this actually means. Suppose two events happen. Call them A and B. Event A, a firecracker explodes in New York. Event B, a firecracker explodes in Los Angeles. Simultaneously, as far as you can tell, with the New York one. You're standing on the ground between them. From your perspective, both firecrackers go off at the same moment. Now someone flies past you in a very fast spaceship, let's say 80% the speed of light, heading from New York toward Los Angeles. Do they also see both firecrackers go off simultaneously? No, they don't. The spaceship observer sees the Los Angeles firecracker go off before the New York one. And here's the critical point. Neither of you is wrong. There is no fact of the matter about which one went off first. Simultaneity at the same time is not absolute. It depends on the observer's state of motion. Einstein worked this out mathematically. Minkowski, his former teacher, went further. In 1908, Minkowski said something remarkable. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. What Minkowski saw is that what's really fundamental isn't space and isn't time. It's space-time, a four-dimensional geometry, where events live as fixed points. Now we're getting somewhere. In ordinary three-dimensional space, if I rotate my coordinate system, turn my head, say the x, y, and z coordinates of an object change, but the actual distance to the object, the quantity, squirt x quartred plus y quartred plus z quartred, stays the same. Distance is invariant under rotation. It doesn't depend on which way you're facing. In space-time, the analogous invariant quantity is the space-time interval. For two events separated by spatial distance d and time difference t, the space-time interval is s quadre equals sign ct quadre minus d quadre. This quantity, unlike time alone, unlike distance alone, is the same for every observer. No matter how fast you're moving, when you calculate s quadre for two events, you get the same number. What this means, when you change your speed, you are rotating in space-time. You're trading time separation for space separation, and vice versa, the way rotating a ruler trades its east-west length for north-south length. The ruler doesn't get shorter, it just points in a different direction. The space-time interval doesn't change, your time and space axes just tip relative to someone else's. And here is where the future comes in. Because now, your present moment is not a universal line slicing through space-time. It's a plane in your coordinate system. And when I change my velocity, that plane tips. The events I call simultaneous with right now shift. If I accelerate toward a distant galaxy, the Andromeda galaxy, 2.5 million light-years away, at a comfortable 1g for a few seconds, the set of events I call right now on Andromeda shifts by thousands of years. In one direction of acceleration, my right now includes events that your right now would call thousands of years in Andromeda's future. Your future events on Andromeda, events that haven't happened yet from your perspective, are already present moment events from mine. That's not poetry, that's what the mathematics of special relativity says, directly and without escape. There's a thought experiment worked out carefully by physicists, not by philosophers, sometimes called the Andromeda paradox. described by Roger Penrose. Two people walk past each other on a street. One is walking toward Andromeda. One is walking away. Their velocities differ by maybe a meter per second. Because of the tipping of their simultaneity planes over 2.5 million light-years, their respective right nows on Andromeda differ by about 80 years. One person's present includes events that are, for the other person, still 80 years in the future. Both present moments are equally valid. Neither is the real one. The conclusion that physicists generally draw from this, and it's not unanimous, there are dissenters, and I'll say why in a moment, is the block universe interpretation. Space-time is a four-dimensional block. Every event that has ever happened or will ever happen exists in that block as a fixed point. Past, present, and future are equally real, not in some mystical sense, but in the same sense that here and there are equally real. You can't visit there right now, but it exists. You can't visit tomorrow right now, but it exists. Your birth exists. Your death exists. Every conversation you've ever had, every thought, every moment, fixed points in four-dimensional space-time. Now, this makes a lot of people uncomfortable. And I understand why. It feels like it rules out free will, like it makes everything predetermined. I want to be careful here because I'm a physicist, not a philosopher, and this question is genuinely outside what I can answer from the equations alone. The equations describe the geometry. They don't tell you whether you experience that geometry as having choices. That's a different kind of question. What I can tell you is that the equations say this: if you want to preserve the idea of a universal present moment, a single now, that's the same for everyone, you have to abandon special relativity, and special relativity has been tested to extraordinary precision. GPS satellites have to correct for both special and general relativistic effects on their clocks, about 38 microseconds per day total, or they accumulate errors of about 11 kilometers per day. Your phone's maps work because we account for relativity. The universe is, as best we can tell, Einsteinian. There's a harder question that the block universe doesn't answer, and I want to be straight with you about it. If past and future are equally real, if they're just different directions in space-time, why does time feel like it goes in only one direction? Why do I remember the past and not the future? Why does the egg scramble and not unscramble? Why does a glass shatter and not spontaneously reassemble? The laws of physics at the microscopic level are time-symmetric. If you film a collision between two billiard balls and play the film backward, both the forward and backward versions satisfy Newton's laws. There's nothing in the equations of electromagnetism or quantum mechanics or even general relativity that picks out a preferred direction for time. The equations work equally well, forward and backward. The arrow of time, the felt, experienced, irreversible direction, comes from entropy. The second law of thermodynamics: closed systems tend toward higher entropy, toward more disorder. An egg is a very low entropy configuration of atoms. A scrambled egg is a higher entropy one. There are vastly more ways to arrange atoms into scrambled egg configurations than into whole egg configurations. So when you break the egg and stir it, you almost certainly move toward higher entropy, and you almost certainly don't accidentally reverse. But why was entropy low to begin with? Why was the early universe in such an extraordinarily low entropy state that 13.8 billion years later we're still running downhill entropically, still have complex structures, still have stars burning, and people thinking? We don't know. That's not false modesty. The low entropy of the early universe. What Roger Penrose estimates required a precision of roughly 1 part in 10 circumflex, 10 circumflex 123, is one of the genuinely unsolved problems in physics. It's where the explanation runs out. The block universe tells you that all of time exists. Entropy tells you why you experience it in one direction. Why entropy was low at one end of the block. That's where we hit bedrock, and honestly say we don't have it yet. So where does this leave us? You are moving through a four-dimensional geometry. The word now refers to a three-dimensional slice of that geometry, and which slice is now depends on your velocity. Change your velocity, and your now shifts, not just your perception of it, but the actual geometry. Events that were in your future can become contemporaneous with your present, and events in your past can become contemporaneous with someone else's future. The star you looked at earlier, Polaris, 433 light-years away. If someone in a very fast spaceship were heading away from Earth right now, there right now on Polaris, would be 433 years in what you'd call Polaris's future. From their present moment, Things are happening on that star that you would call events that haven't happened yet. Those events exist. They're points in space-time. They're just not in your now. The more precise statement of the thing I said at the start, your future already exists, is this. The events that will constitute your future are already fixed points in four-dimensional space-time. They are, to observers with different velocities, already contemporaneous with different moments of their experience. There is no coherent observer-independent sense in which those events don't exist yet. This should feel strange. If it doesn't feel strange, you haven't fully absorbed it. What I find genuinely remarkable, and this is the thing that keeps me up, in the good way, is that we figured this out by asking a simple question: what does it mean for two events to happen at the same time? Newton assumed there was a simple universal answer. Michelson and Morley ran an experiment. The answer was nothing like what anyone expected. Einstein followed the math. Minkowski geometrized it. And we ended up with a universe that is, in a very specific technical sense, timeless. A block in which everything that has ever happened or will happen is equally, permanently, geometrically real. We did not go looking for this. The universe just turned out this way, and it will go on being this way, whether you find it comfortable or not, which is frankly one of the things I love most about physics.